In the vast expanse of a universe, galaxies drift through the darkness like leaves carried on a cosmic river. For centuries, humanity has gazed at the night sky, marveling at stars, nebulae, and distant galaxies, assuming the universe was mostly uniform and predictable. Yet beneath the familiar constellations, hidden behind the veil of our own Milky Way, lies a force that challenges everything we thought we knew about cosmic motion. Astronomers call it the Great Attractor, a mysterious region of space exerting a gravitational pull so immense that it is dragging entire galaxies, including our own Milky Way, toward it at breathtaking speeds. Unlike the bright galaxies we can see with telescopes, the Great Attractor is invisible to the naked eye. It hides in a region astronomers call the zone of avoidance, obscured by dense clouds of stars and cosmic dust in the plane of our galaxy. Optical telescopes see only darkness, but the universe does not hide its secrets completely. The presence of the Great Attractor is revealed not by light, but by motion, a subtle, coordinated drift of galaxies over hundreds of millions of light years. It is a whisper of gravity on the grandest scales, a force that cannot be ignored, and yet remains frustratingly elusive. Discovered in the late 20th century through careful observations of galaxy velocities, the Great Attractor transformed our understanding of the local universe. Galaxies are not simply moving apart. Due to cosmic expansion, they're also being gently pulled along unseen currents toward regions of immense mass. The Milky Way, along with neighboring galaxies in the local group, hurtles through space at over 600 kilometers per second, inexorably drawn toward a destination we cannot directly observe. It is a motion that has persisted long before the birth of our sun, long before life existed on Earth, and will continue for eons to come. At the heart of this cosmic enigma lies the Norma Cluster, a massive congregation of galaxies surrounded by hot gas and an unseen halo of dark matter. Yet even Norma cannot explain the full gravitational tug. The Great Attractor is part of a larger supercluster of galaxies known as Laniakea, a sprawling network of matter stretching across hundreds of millions of light years. In this gravitational basin, galaxies flow along invisible streams, pulled toward nodes of immense mass. These nodes, interconnected by filaments of dark matter, form the cosmic web, the unseen structure that organizes the universe on its largest scales. The Great Attractor forces us to confront profound truths about the universe. It demonstrates that motion, not stillness, is the default state of cosmic structures. It reminds us that dark matter, invisible yet dominant, shapes the paths of galaxies across unimaginable distances. And it challenges our perception of cosmic centrality. There is no singular center of a universe, only temporary gravitational wells where matter converges before dark energy eventually drives everything apart. Yet beyond the science lies a deeper story, a story of perspective, of scale, and of our place in a universe in motion. The Great Attractor is a reminder that we are not isolated observers. We are participants in a vast, unfolding drama that has been playing out for billions of years. The Milky Way is not simply a static home in space. It is a traveler, part of a great cosmic flow, carried along by forces that stretch across hundreds of millions of light years. Understanding the Great Attractor is not just about mapping galaxies. It is about understanding the unseen currents that shape the destiny of everything in the universe. In the chapters that follow, we will journey into this hidden realm. We will uncover how the Great Attractor was discovered, what structures lie at its core, and how it connects to even larger formations like the Shapley Supercluster. We will explore the roles of dark matter and dark energy, the invisible architects of cosmic motion, and we will ask the ultimate questions. Why are galaxies moving the way they are? What does this tell us about the past, present, and future of the universe? And most importantly, what does it reveal about our place in a cosmos in motion? The Great Attractor may be invisible, but its presence is undeniable. It is a quiet, persistent force shaping the paths of galaxies, and through it, It shapes our understanding of reality itself. To glimpse it is to glimpse the universe's hidden architecture, a vast web of matter and motion, where even the tiniest human perspective is part of something infinitely larger. Far beyond the familiar stars of our night sky, beyond the spiral arms of the Milky Way, and even beyond the comfortable maps of our known universe, there exists a region of space exerting a gravitational influence so immense that entire galaxies are being dragged toward it. Astronomers call it the Great Attractor, not because we fully understand it, but because we cannot ignore its pull. It is not a single object we can point to, not a glowing beacon or a visible monster in space, but rather a gravitational anomaly so powerful that it distorts the motion of galaxies across hundreds of millions of light years. Our galaxy, the Milky Way, is not standing still. Along with our neighboring galaxies in the local group, we are moving at a staggering speed of over 600 kilometers per second relative to the cosmic microwave background, the faint afterglow of the Big Bang. This motion is not random. It has direction. It is as if the universe itself is gently, but relentlessly, tugging us towards something hidden. That something lies in the general direction of the Centaurus and Norma clusters, deep within a region astronomers ominously call the zone of avoidance. The zone of avoidance is a thick cosmic blindfold. It is the part of the sky obscured by the dense dust, gas, and stars of our own Milky Way galaxy. Optical telescopes struggle to see through it, making it one of the least explored regions of the observable universe. Ironically, this blindness is exactly where the gravitational signal grows strongest. Galaxies on every side appear to be flowing inward, like leaves carried by an invisible cosmic current. What makes the Great Attractor truly unsettling is not just its size, but its secrecy. Unlike black holes or galaxy clusters we can observe directly, the Great Attractor refuses to reveal itself easily. It does not shine. It does not announce its presence with spectacular light. Instead, it reveals itself only through motion through the strange, coordinated drift of galaxies that should otherwise be moving apart due to cosmic expansion. This discovery challenged one of our most fundamental assumptions, that on the largest scales, the universe expands smoothly and uniformly. Instead, the Great Attractor suggests that massive structures still dominate cosmic motion, bending space and time long after the Big Bang's initial explosion. It hints that gravity, even across incomprehensible distances, still rules the cosmic landscape. But what exactly is pulling us? Is it a colossal cluster of galaxies hidden behind the Milky Way? A supercluster so massive it reshapes the flow of the universe? Or something even stranger, something we have yet to fully comprehend? To answer these questions, astronomers had to abandon visible light and turn to radio waves, infrared surveys, and X-ray observations. Only by peeling back the layers of cosmic dust could humanity begin to glimpse the true nature of this gravitational giant. And what they found was both enlightening and deeply humbling, because the Great Attractor is not merely a destination in space. It is a clue, a signpost pointing toward the largest structures ever formed, and a reminder that even our cosmic neighborhood is shaped by forces far beyond our everyday perception. And this is only the beginning. The story of the Great Attractor did not begin with a telescope pointed at a glowing object in the sky. Instead, it began with numbers that refused to behave. In the 1970 and early 1980, astronomers were carefully measuring the velocities of galaxies, attempting to map how the universe expands. According to the simplest version of cosmic expansion, galaxies should move away from each other smoothly, their speeds increasing with distance, as described by Hubble's law. But when scientists examined nearby galaxy clusters, something felt wrong. Galaxies were not moving exactly as expected. Many of them showed what astronomers call peculiar velocities motions that deviated from the smooth expansion of the universe. Instead of drifting calmly outward, large groups of galaxies appeared to be flowing together, converging toward a single region of space. The effect was subtle at first, But as data improved, the pattern became undeniable. By the early 1980s, two astronomers, Alan Dressler and Sandra Faber, along with their collaborators, began analyzing galaxy motions across vast distances. What they found was astonishing. Galaxies across a region more than 300 million light-years wide were moving in a coordinated way. Even more unsettling was the direction of this movement. It pointed straight toward a region hidden behind the Milky Way's dense disk, an area no optical telescope could easily penetrate. This was not a local disturbance. It was not caused by a nearby galaxy or even a single galaxy cluster. The pull was too strong, too widespread. To explain the observed velocities, astronomers calculated that the unseen mass responsible would need to be equivalent to tens of thousands of Milky Way galaxies combined. Whatever lay there had to be among the most massive structures in the observable universe. The name Great Attractor was born not from certainty, but from necessity. It was a placeholder, a scientific admission that something enormous existed, even if its nature remained unknown. Unlike black holes, whose effects are violent and localized, the Great Attractor worked quietly, shaping the motion of galaxies across cosmic time without revealing its face. As researchers refined their measurements, the picture grew clearer and more disturbing. Our own galaxy was part of this flow. The Milky Way, along with the Andromeda Galaxy and dozens of others in the local group, was moving toward this mysterious region at an extraordinary speed. We were not merely observers. We were participants in a gravitational dance. Yet the discovery raised an uncomfortable question. How could something so massive remain hidden? In a universe filled with glowing stars and radiant galaxies, how could an objector structure of such scale escape detection? The answer lay in the cosmic geography of our galaxy. The Milky Way's disk blocks nearly 20% of the extragalactic sky, creating a blind zone where even the largest structures can remain concealed. To overcome this limitation, astronomers turned to new tools. Radio telescopes could detect hydrogen gas clouds. Infrared observatories could peer through dust. X-ray telescopes could spot the hot gas trapped in massive galaxy clusters. Piece by piece, a hidden cosmic landscape began to emerge from behind the veil. But what they found was not a single object. It was something far more complex and far more revealing about the universe's true architecture. Because the Great Attractor was not alone. It was part of something bigger. As astronomers pushed deeper into the hidden regions of the sky, a crucial realization emerged. The Great Attractor was not a single object, not a cosmic vacuum cleaner pulling everything toward point. Instead, it was the gravitational signature of an enormous concentration of mass, spread across a vast region of space. This discovery fundamentally changed how scientists understood the structure of the universe. At the heart of the Great Attractor lies a massive cluster of galaxies, known as the Norma Cluster, or Abell 3627. Located approximately 220 million light-years away, this cluster contains thousands of galaxies bound together by gravity and surrounded by vast amounts of hot gas and dark matter. In many ways, the Norma Cluster rivals the famous Coma Cluster, one of the most massive galaxy clusters known. The difference is that Coma shines brightly in the sky, while Norma hides behind the thick veil of the Milky Way. But even the Norma Cluster alone could not fully account for the observed gravitational pull. Calculations showed that its mass, immense as it is, fell short of explaining the large-scale galaxy flows. This meant the Great Attractor was not just a cluster, it was part of a much larger structure, one that stretched across hundreds of millions of light-years. This structure is known as the Laniakea Supercluster, a vast cosmic region that includes the Milky Way, the Virgo Cluster, and dozens of other galaxy groups. Laniakea, meaning immense heaven in Hawaiian, is not a rigid object, but a gravitational base in a region where galaxy motions flow inward toward a common center. And that center lies very close to the Great Attractor. In this sense, the Great Attractor is not the ruler of Laniakea, but its gravitational low point, much like a valley where rivers naturally converge. Galaxies are not being violently pulled inward. They're gently drifting along the curved fabric of space-time, following paths laid out billions of years ago during the universe's early formation. What makes this realization profound is that it reveals the universe to be far from uniform. On the largest scales, matter is arranged in a cosmic web of vast network of filaments, walls, and voids. Galaxies are not scattered randomly, but trace these filaments like beads on invisible strings. The Great Attractor is where several of these filaments intersect, creating a node of extraordinary mass. Dark matter plays a crucial role here. Most of the mass responsible for the Great Attractor's pull is invisible, detectable only through its gravitational effects. Without dark matter, the observed motions of galaxies simply would not make sense. In fact, the Great Attractor serves as one of the strongest pieces of evidence that dark matter dominates the large-scale structure of the universe. Yet even as the Great Attractor became more defined, another surprise emerged. The flow of galaxies did not stop there. Beyond the Great Attractor, even larger motions appeared, movements suggesting the presence of an even more massive structure further away. This raised a startling possibility. The Great Attractor might itself be moving towards something bigger. If true, this would mean the universe's hierarchy of structures extends far beyond what we once imagined. Superclusters feeding into even greater concentrations, all shaped by gravity and dark matter on unimaginable scales. And so, the Great Attractor transformed from a mystery into a gateway, a sign that our cosmic map was still incomplete. To truly understand the Great Attractor, we must step beyond visible galaxies and enter the realm of the invisible forces that dominate the universe. Everything we can see, stars, planets, nebulae, galaxies, account for less than 5% of the universe's total content. The rest is composed of dark matter and dark energy, and the Great Attractor sits precisely at the crossroads where their effects become dramatically visible. Dark matter is the silent architect of cosmic structure. It does not emit, absorb, or reflect light. It outweighs normal matter by a factor of 5. In the region of the Great Attractor, dark matter forms massive halos that surround galaxy clusters and bind them together. These halos act like gravitational scaffolding, allowing clusters such as the Norma Cluster to grow far larger than visible matter alone would permit. Without dark matter, galaxies would fly apart, and the Great Attractor simply could not exist. The observed galaxy flows measured across hundreds of millions of light-years match simulations only when dark matter is included. In this sense, the Great Attractor is not just a gravitational anomaly. It is a direct demonstration of dark matter's dominance over the cosmic landscape. But gravity is not acting alone. On even larger scales, the universe is driven apart by dark energy, a mysterious force responsible for the accelerating expansion of space itself. Discovered in the late 1990s, dark energy works against gravity, pushing galaxies away from each other faster and faster over time. This creates a cosmic tug-of-war, gravity pulling matter together, dark energy pushing space apart. The Great Attractor exists in a narrow window where gravity still wins. At distances of a few 100 million light-years, gravitational attraction from massive structures like Laniakea can overcome cosmic expansion, guiding galaxies into coherent flows. But beyond a certain scale, dark energy dominates completely, and even the most massive structures lose their ability to influence motion. This means the Great Attractor is not eternal. Its influence will weaken as the universe continues to expand. This balance answers a crucial question. Is the Great Attractor pulling galaxies against the expansion of the universe? The answer is both yes and no. Galaxies are still receding from one another overall, but their paths are subtly curved by massive structures, much like leaves drifting down a river that itself flows outward. The Great Attractor shapes direction, not destiny. What makes this especially fascinating is that the Great Attractor provides astronomers with a natural laboratory. By studying galaxy motions here, scientists can test theories of gravity, dark matter distribution, and cosmic expansion all at once. Any mismatch between observation and theory would hint at new physics. And there have been hints. Some studies suggest that galaxy flows extend beyond the Great Attractor toward an even larger structure known as the Shapley Supercluster, a colossal concentration of galaxies located more than 650 million light-years away. If true, this would imply that the Great Attractor is only one gravitational waypoint in a much grander cosmic migration. This raises a humbling possibility that even the largest structures we know are merely tributaries in an even greater cosmic river. And if that is the case, then the Great Attractor is not the end of the story. It is the beginning of a deeper mystery. As astronomers extended their maps farther into the depths of space, a striking realization emerged. The Great Attractor, powerful as it is, may not be the final destination of galactic motion. Instead, it appears to be part of a larger gravitational current, one that flows toward an even more massive and distant structure, the Shapley Supercluster. The Shapley Supercluster is one of the most massive concentrations of galaxies ever discovered. Located roughly 650 to 800 million light-years away, it contains more than 8,000 galaxies packed into an immense region of space. Its total mass is estimated to be over 10 million billion times the mass of the Sun, making it one of the densest nodes in the cosmic web. Compared to Shapley, the Great Attractor begins to look less like a final pull and more like a stepping stone. Measurements of galaxy velocities suggest that a significant portion of the motion once attributed solely to the Great Attractor may actually be influenced by Shapley's far-reaching gravitational field. Galaxies flow first toward the dense region near the Norma Cluster and then continue onward, subtly redirected by the immense mass beyond. This layered influence reveals that cosmic motion is not controlled by isolated structures, but by overlapping gravitational basins operating on different scales. This discovery forced cosmologists to confront a deeply ingrained misconception, the idea of a center of the universe. The Great Attractor often gets described in popular media as a center, but scientifically, this is misleading. The universe has no central point. The Big Bang did not explode from a location in space. It occurred everywhere at once. What we observe instead are local centers of mass, regions where gravity temporarily overcomes expansion. The Great Attractor is one such region. The Shapley Supercluster is another larger and more distant. Together, they illustrate how the universe organizes itself hierarchically, with smaller structures feeding into larger ones, much like streams flowing into rivers, rivers into seas, and seas into oceans. These cosmic flows also provide strong evidence for the cosmological principle, the idea that the universe is homogeneous and isotropic on the largest scales. While matter clumps locally, there is no preferred direction or ultimate attractor governing everything. Each region experiences its own gravitational landscape, shaped by the distribution of dark matter and galaxies nearby. What makes this picture especially elegant is that it aligns beautifully with simulations of cosmic evolution. Computer models that start shortly after the Big Bang and include dark matter naturally produce vast filaments, superclusters, and voids. The Great Attractor and Shapley Supercluster emerge not as anomalies, but as inevitable outcomes of gravity working over billions of years. Yet despite this progress, many questions remain unanswered. How much of the galaxy flow is due to Shapley versus other unseen structures? Are there even larger mass concentrations beyond our current observational limits? And most intriguingly, are we seeing the universe as it truly is, or only the portion illuminated by our limited instruments? The Great Attractor, once feared as an unknown cosmic threat, now appears as a signpost pointing towards something even greater. It reminds us that every time we think we've reached the edge of understanding, the universe quietly reveals another layer. And still, one question lingers in the human imagination. Is the Great Attractor dangerous? The name Great Attractor has an almost ominous quality, and it has fueled countless misconceptions. To the untrained ear, it sounds like a cosmic predator, something pulling galaxies toward destruction, perhaps even threatening Earth itself. But this fear arises from misunderstanding both scale and time in the universe. First, the most important truth: the Great Attractor is not dangerous. It is not a black hole. It is not a collapsing region of space-time. And it is certainly not something that will swallow the Milky Way. The motion toward the Great Attractor is slow, subtle, and measured in hundreds of millions to billions of years. Even at speeds of hundreds of kilometers per second, the distances involved are so vast that nothing dramatic will happen on human, planetary, or even stellar timescales. Our galaxy has been moving toward this region since long before the Earth existed. Dinosaurs rose and fell, continents drifted, stars were born and died, all while the Milky Way quietly followed the gravitational contours of its cosmic neighborhood. This motion does not signal an impending collision or collapse. It is simply gravity doing what it has always done. Another common myth is that the Great Attractor violates the expansion of the universe. In reality, it coexists perfectly with cosmic expansion. The universe is expanding everywhere, but expansion does not erase gravity. On smaller scales, galaxies, clusters, superclusters, gravity still binds matter together. The Great Attractor exists well within this gravitationally connected regime. Some fear that the Great Attractor represents a flaw in cosmology, a sign that our theories are broken. In fact, the opposite is true. The observed galaxy flows align remarkably well with predictions from lambda-CDM cosmology, the current standard model of the universe. Far from being an anomaly, the Great Attractor confirms that dark matter behaves exactly as expected on large scales. There's also the myth of inevitability, the idea that everything is falling toward one final point. This is a misunderstanding of cosmic flows. Galaxies move within gravitational basins, but these basins themselves evolve. Over time, dark energy will stretch space so rapidly that even superclusters like Laniakea will become gravitationally isolated. The Great Attractor's influence will fade, not intensify. Perhaps the most fascinating psychological aspect of the Great Attractor is what it reveals about us. Humans instinctively search for centers, causes, and ultimate destinations. We want the universe to have a focal point, a hidden engine driving everything. The Great Attractor seems to offer that narrative, but nature resists simplicity. There is no cosmic throne at the heart of creation, only patterns emerging from gravity and time. Yet the Great Attractor remains deeply important, not because it threatens us, but because it teaches us how the universe organizes itself. It shows that motion has memory, that the early universe's tiny density fluctuations grew into vast structures that still shape our trajectory today. In this way, the Great Attractor is less like a monster and more like a fossil record of how the universe grew up. And as our instruments improve, we may soon see it more clearly than ever before. For decades, the Great Attractor remained shrouded in mystery, not because it was unknowable, but because it was hidden behind our own galaxy. The Milky Way, beautiful as it is, acts like a cosmic curtain, blocking visible light from the very region where the gravitational signal is strongest. To move forward, astronomers had to learn how to see the universe without relying on sight alone. Radio astronomy became one of the first breakthroughs. By detecting the faint 21-centimeter emission line of neutral hydrogen, scientists could map galaxies that were otherwise invisible. These surveys revealed vast structures lurking behind the zone of avoidance, confirming that the region was far from empty. Instead, it was packed with galaxies moving in coordinated flows, exactly what the Great Attractor hypothesis predicted. Infrared telescopes pushed this understanding even further. Instruments like IRAS, 2MASS, and later space-based observatories could pierce through dust that blocks visible light. They revealed galaxy clusters, filaments, and walls forming a continuous structure across the sky. What once appeared as a blank region was now recognized as one of the most crowded and dynamic parts of the nearby universe. X-ray astronomy added another layer of confirmation. Massive galaxy clusters trap vast reservoirs of superheated gas that glow brightly in X-rays. The Norma Cluster emerged as one of the strongest X-ray sources in the region, confirming its enormous mass and its central role in the Great Attractor's gravitational field. These observations left little doubt. The Great Attractor is real, measurable, and deeply embedded in the cosmic web. The next generation of telescopes promises even greater clarity. The Square Kilometer Array, SKA, will map hydrogen across unprecedented distances, allowing astronomers to trace galaxy motions with extraordinary precision. Meanwhile, space missions focused on dark energy and large-scale structure will refine our understanding of cosmic flows, potentially revealing how structures like the Great Attractor evolve over time. Perhaps most exciting is the role of gravitational lensing. By observing how massive structures bend the light of distant galaxies, scientists can directly map dark matter even when no visible matter is present. Applying these techniques to the Great Attractor region could finally reveal its full mass distribution, ending decades of uncertainty. But beyond the technical achievements lies a deeper implication. The Great Attractor helps scientists understand the future of structure. In the universe, over billions of years, gravity will bind galaxies into ever larger systems until dark energy ultimately halts this growth. Superclusters like Laniakea are among the largest structures that will ever form. In the far future, they will become isolated island universes, drifting apart from all others. In this context, the Great Attractor is a snapshot a moment in cosmic history when gravity still had the upper hand locally. It shows us the universe in transition, balance between growth and dispersal. And that brings us to the final philosophical question. What does it mean that we are being pulled? Despite decades of observation and increasingly powerful instruments, the Great Attractor remains incomplete in our understanding. We have mapped parts of it, measured its influence, and identified major contributors like the Norma Cluster and the Laniakea Supercluster. Yet when scientists compare observations with simulations, subtle discrepancies remain whispers that the story is not fully written. One of the greatest uncertainties lies in how much mass is truly hidden in the Great Attractor region. Dark matter dominates the structure, but its exact distribution is still unclear. Some models suggest there may be additional massive filaments or clusters lurking behind the Milky Way, still invisible even to infrared and radio surveys. If these structures exist, they could significantly alter our understanding of local cosmic flows. Another open question concerns bulk flow velocities, the collective motion of galaxies over vast scales. Some studies have reported galaxy motions that seem larger and more coherent than standard cosmology predicts. If confirmed, this could point to physics beyond the current lambda-CDM model, perhaps involving unknown properties of dark matter or subtle modifications to gravity itself. There is also the mystery of cosmic alignment, the direction of our galaxy's motion, the dipole anisotropy of the cosmic microwave background. And large-scale flows all seem to share a common axis, pointing near the Great Attractor and beyond. While this may be coincidence, some researchers wonder whether it hints at deeper correlations in the universe's large-scale structure remnants of primordial conditions from the earliest moments after the Big Bang. Even the boundaries of Laniakea remain under debate. Superclusters are not solid objects. They're defined by motion, not walls. As new data arrives, the gravitational contours may shift, revealing that our cosmic home is larger, smaller than currently believed. The Great Attractor could move from being a central feature to merely one node among many in an even greater basin. Perhaps the most profound unknown is how typical our situation is. Is every galaxy part of a similar flow toward massive hidden structures? Or are we living during a rare cosmic configuration where gravity and dark energy are temporarily balanced in just the right way for such structures to be observable? These unanswered questions remind us that astronomy is not a finished book. It is a living investigation, Each answer sharpens the mystery rather than dissolving it. The Great Attractor, once feared as a dark enigma, has become a frontier, a place where observation, theory, and imagination meet. And it is precisely because we do not yet know everything that the final part of this story matters. Because understanding the Great Attractor is not just about mapping galaxies. It is about understanding how humanity learns its place in an ever-unfolding universe. When all equations are written, when all maps are drawn, and when all myths are stripped away, the Great Attractor stands not as a cosmic monster, but as a quiet truth about how the universe works. It reminds us that the universe is shaped less by spectacle and more by patience be forces acting steadily over unimaginable spans of time. The Great Attractor does not announce itself with explosions or light. It reveals its presence. Through motion, through galaxies gently bending their paths, through subtle deviations in velocity, through patterns only visible when millions of observations are combined into a single cosmic perspective. In this way, it teaches us that the deepest realities of the universe are often invisible, known only through their effects. Our journey toward this region is not a voyage we will ever complete. The distances are too vast, the timescales too long, and the universe itself is changing too rapidly. Long before the Milky Way could ever approach the Great Attractor, cosmic expansion driven by dark energy will isolate us from it entirely. The pull we feel today is a relic of a younger universe, one where gravity still had a stronger voice. And yet, this knowledge does not make the Great Attractor insignificant. On the contrary, it makes it precious. It is a snapshot of cosmic structure at its largest scale, a fossil imprint of how matter organized itself after the Big Bang. By studying it, we study the universe's memory. There is something deeply humbling in realizing that our galaxy is moving, not by choice, not by design, but by the simple curvature of space-time. We are passengers on a cosmic current, carried along by forces set in motion billions of years ago. The Great Attractor is not pulling us toward an ending, but reminding us of our connection to everything else. In human history, we once believed the heavens were fixed and eternal. The Great Attractor shatters that illusion. Even galaxies drift. Even superclusters evolve. Motion is universal, and permanence is the exception. Perhaps the most profound insight is this. The universe does not revolve around us, but it includes us. The same gravity that shapes the largest structures also governs the fall of an apple, the orbit of the moon, and the formation of stars within our own galaxy. The Great Attractor is not separate from us. It is part of the same cosmic law that made us possible. So when we look up at the night sky, we are not just seeing where we are. We are seeing where we are going. Not toward destruction, not toward a center, but along a vast, elegant flow written in gravity, shaped by time, and revealed through understanding. And in that understanding, the Great Attractor becomes more than a mystery. It becomes a reminder we belong to a universe in motion.